Our project is a swappable battery management system designed for electric vehicles. In the next section, we'll take you through how our system works. Imagine a subscriber of our system is driving their electric vehicle. While on the road, they notice that their battery level is getting low. Instead of waiting for hours at a traditional charging station, they use our mobile application or in-vehicle interface to quickly search for the nearest battery swapping station. Once a nearby station is located, they drive to the facility. Upon arrival, the user begins the authentication process. After successful authentication, the user removes the discharged battery packs from their vehicle. These empty or low-energy batteries are placed into specially designed slots at the station. The station then provides fully charged, tested batteries. The user installs them and is ready to go all within minutes, much faster than traditional charging. After the swap, the system updates the user's profile with details like time, location, and battery status. There are three main objects in our project: make a BMS for every pack, a central unit for connecting those packs, and making a swapping station where the swiping is happening. In the vehicle side, all the BMSs are connected to central unit, and from that we can enable discharging and getting the readings. In the docking station, every slot has an interface unit. They are connected to control unit and it is communicate with central unit. There are three main deliverables in our project: SD docking station, BMS for battery pack, and central unit. Docking station is the unit where the swapping is happening. Billing is done according to SOC of batteries. There are two main boards in here: adapter board and battery interface unit. Now I talk about the BMS for each battery pack. This picture shows the high-level architecture of the vehicle and battery connection. In our design, the BMS board contains only the essential components, while the central unit includes the parts common to all BMS units. We use the BQ79656 IC to monitor voltages of 16 cells and temperatures at 7 points, preventing thermal runaway. Charging current is controlled using a buck converter. A contactor handles discharge cutoff and communication. For active cell balancing, we use the low-power ETA3 LOIC. A fuel gauge ensures accurate state of charge measurement. We use CAN communication for reliable data exchange between the BMS and central unit. The STM32F1i3 MCU manages the system via CAN, UART for cell data, and I2C for the EEPROM and fuel gauge. A 1A output from the battery powers all components. Each BMS has a unique ID for secure authentication. We designed the BMS in three separate parts: monitoring IC with MCU active balancing unit, charging current limiting unit. Now, let me explain the updates made to the monitoring IC with MCU unit. This is our 4-layer PCB design, where we have correctly implemented isolation, managed signal interruption, optimized track width for high current paths, and incorporated reference planes to reduce noise. This is the monitoring IC user interface. Now we will see active cell balancing unit. If we consider series connected cells, when we charge or discharge the batteries, due to their capacity tolerance, their voltages will not same after some time. In other words, the lowest capacity value of cell will overcharged or over-discharged. That is why series-connected batteries need cell balancing while charging and discharging. For active cell balancing, we use ETA3 LOIC, which can balance to series-connected cells using an inductor. These ICs can be cascaded to balance more than to series-connected cells. This is the PCB layout of the active cell balancer. Now let's see charging current limiting design. At the charging station, multiple batteries are connected to a single charger. While the charger can supply more than 20 ampere, the BMS limits the current to 20 ampere for safety. Similarly, in the vehicle, batteries are connected in parallel. To protect the system, we prevent low voltage packs from drawing charge from higher voltage ones, ensuring safe and reliable operation. This is our PCB design of current limiting circuit. The central unit is inside the vehicle and it is responsible to communicate with each BMSS. In the firmware development, we mainly focus on three factors, such that authentication, protection, and real-time data communication. Authentication is done using HMACSHA-256 algorithm-based random challenger mechanism. For communication, we use CAN bus and we had make some custom CAN protocols for that. To visualize and edit threshold values of the BMS, we made a Windows application along with this. Thank you.